So this is signal integrity analysis in printed circuit boards. What is signal integrity? Signal integrity, also known as SI, refers to the properties in a digital system that measure the quality of an electrical signal to any select component. The signal integrity of an electrical signal can become corrupt due to a variety of reasons, including reflections caused by impedance mismatch, crosstalk caused by inductive and capacitive coupling, and time delay between lines. Why is signal integrity so important? As we as a world evolve, the need for more robust and elegant technology becomes more critical. This poses challenges such as the increased number of chips on a PC board and the speed of the board's respective chips, the scaling of wires and chips effectively by Moore's law, the reduction of off-chip power supply distribution, and the escalation of clock rates and thinner metal layers. Because of such and a variety of more constraints put in place on this ever-growing technological world, we need a methodology put in place to quantify, analyze, intercede, and rectify the quandaries caused by signal integrity. There are a variety of techniques one can use to quantify and correct signal integrity issues. The first and most notable is the time domain reflectometer as shown in the figure below. A basic time domain reflectometer consists of a source impedance at the beginning of the source followed by the rest of the line. The time domain reflectometer technique is widely used due to the fact that it can measure reflections from impedance mismatch and can also measure time delay. Another way to quantify and measure signal integrity is through the use of an eye diagram. Eye diagrams are primarily used in determining quantities such as bit error rate, signal to noise ratio, jitter, and crosstalk. Crosstalk in signaling systems can be measured most notably by quantifying the eye height and the eye width. Shown below is an LT-SPICE model of a printed circuit board. The inductive and capacitive coupling is representative of the distance between each trace and allows one to simulate signal integrity issues that are unwanted. For this purpose, however, we desire such coupling to see the effects of crosstalk, time delay, and reflections. We can simulate this circuit board in practicality by using the PC board shown below, where the exact LT-SPICE schematic has been developed into a real board. So shown here is our basic TDR measurement setup. We have the oscilloscope attached to the source of the line, and then this is measured in open circuit configuration. So here we have the original step with a period of 1.6 microseconds and a voltage peak to peak of 3.3 volts. This picture shows the PC board in which we measure the time delay from source to termination, where the source will always be the reference point. Now we are going to measure the time delay at line 1 of the circuit. So this is our current configuration for that setup. We have an oscilloscope at the source, and then we have an oscilloscope at the end, and then we can compare the two and measure the time delay of the line. So to measure the time delay of at the source to line 1, you take the rise time of the source, which is in red, and the rise time of the line 1, which is in yellow, and we get the difference of the two, which is 425 nanoseconds. And then we then get the rise time of the source to the fall time of the source to the fall time of the line, and then we compare that and we get 435 nanoseconds. And then we would take the average of the two to get the time delay, the total time delay of line 1. Shown below is the configuration for the PC board in which we view the reflections from an open circuit termination. So this is the TDR measurement at the source with an open circuit termination. Some open circuit terminations are used to reduce power dissipation and also to take advantage of the voltage doubling effect. The following is the configuration for the PC board in which we view the reflections from a short circuit termination.
Now here is our short circuit termination circuit.
Now, if we short circuit the end of the line, then the voltage at the end of the line gets completely reflected, and this has to do with the short circuit termination.
In this picture, the PC board in which we view the reflections from an impedance matched termination. In short, there should be no reflections and the source should be unaffected.
Now here is our matched termination, where we have a termination impedance of 50 ohms.
So now, if you see here, if we match the termination of the line, which is 50 ohms, then we basically, there are 0 reflections. Although there is some here, so it's not perfectly matched, but it's pretty close to where it resembles that of the original wave.
Shown here is the configuration for the PC board in which we measure the crosstalk from line 1 to line 2, or also known as aggressor to victim.
So this is our circuit setup of measuring in comparison the crosstalk of line 1 to line 2.
So we want to measure the crosstalk from line 1 to line 2, which would be aggressor to victim. So therefore, in order to do so, I click trigger, I make source 1 and source 2, and I trigger it on both edges. So see here, I have source 2 trigger on both edges, and source 1 trigger on both edges. Then, from there, I select persistence, and I make persistence infinite. So from there, basically what we're doing is we're getting an eye diagram. And from there, I set the trigger level, so that way I get a good representation of the eyes. For example, if I want to measure the eye width, I would put my cursors over the eye and measure the time difference between the two, which we get 810.47 nanoseconds. Now, in regards to the eye width of line 2, I kind of want to set the voltage up, auto, and then stop it. So for this, I want to put my cursor on analog 1 and cursor channel on analog 2, auto, and then stop. And then I shall get an eye width of 821.20 nanoseconds. Now from there, an important part of the eye diagram is the height. So therefore, I want to measure voltage, and I will first measure the line 1 eye height. So what I want to do is I want to put my cursor, and set my cursor 1 up to the highest eye height, and then from there I want to put my second cursor to the lowest eye height. And I get a Y difference of 4.82 volts. So from there, I then want to measure the eye height of line 2. So from there, I take my cursor, make sure that your voltage divisions are the same, and then measure the top of this with the bottom of this. So therefore, I get a difference of 704 millivolts, which basically tells me that due to the capacitive coupling and the inductive coupling in the circuit, this is causing noise to decrease the voltage peak to peak of line 2.
The following is the configuration for the PC board in which we measure the crosstalk from line 1 to 3.
This is measuring the crosstalk of line 1 to line 3.
So now if I were to do line 3, just going to quick change this. And then I'll clear the display. So for the width of the one, should get the same thing. But now for the width of the other, click stop, and I measure these 2 points. The eye width is approximately 323.94 nanoseconds. And one can also notice as you go further and further down the line, the number of harmonics actually increases. So now what I want to do is I want to measure the eye height of the third line. So what I'm going to do it's easier to see, I'm going to change the volts per division to make it higher. That way I can read this. And then I'm going to measure the voltage, but I'm going to measure at channel 1. Because otherwise, if I don't, I'll get an inaccurate measurement. And I get approximately a height of 426 millivolts. And if you want to see it with the eye diagram, I'll stop this. And it's approximately 400 millivolts. So this just kind of shows you the effect of capacitive and inductive coupling as you go down the line, and also how the harmonics increases. It decreases, crosstalk also decreases the eye width and the eye height as well.
In this picture, the configuration is shown for the PC board in which we measure the crosstalk from line 1 to line 4.
And this is measuring the crosstalk of line 1 to line 4.
Now, my final, I will do measure the line 4. So I'm going to click normal. And I'm going to measure the eye height of line 4. So I get an eye height of 474 millivolts. And if I want to measure the time, I'll measure the time, cursor 1, and measure the eye width, which I get 270.29 nanoseconds, which basically shows you that as you go down the line, again, the eye height decreases and the eye width decreases as well. And you see here in comparison to the last one, the number of harmonics increase as well.
So this circuit was previously done with LT splice. So the green waveform is the waveform at the source, and the blue waveform is the waveform at the termination. And so with the open circuit termination, you can see that the forward traveling wave is fully reflected. So this is with the short circuit termination. So the green waveform is the step at the source, and the blue waveform is the waveform that's fully reflected back. So you can see that the blue waveform is equal and opposite to that of the input waveform. So this is the comparison of the crosstalk between each line. So the pink waveform is our ideal, So that is our ideal crosstalk waveform. And then the red, green, blue, and cyan waveforms are measured at each node, each termination. And these are the waveforms with capacitive and inductive coupling. So the red waveform is the crosstalk at line 1. The green waveform is the crosstalk at line 2. The blue waveform is the crosstalk at line 3. And the cyan waveform is the crosstalk at line 4. So as you can see, as you go down through each line, the crosstalk gets worse and worse and worse because the eye height and the eye width decrease. So this is just some of our comparisons of our measures for the time delay and the eye diagram. So the first table is the LT splice measurements, and the second table is the PCB measurements. So LT splice is kind of an ideal software, so it's not really representative of some of the effects that might happen in a real-time simulation. So therefore, that's why we get some differential between the two. In conclusion, the time domain reflectometer as well as the eye diagram proved to be of significant use in measuring and quantifying signal integrity. Such characteristics are often overlooked in PCB and/or system design, and determining and measuring these characteristics are essential in high-speed digital system design.